We are here going to talk about the basic of a coil. Over here we see a coil and we have some magnetic fields, the red one, and also here we have a coil, but this one has a core. Over here we only got, for example, air in a space, but here we have an iron core, which results that the magnetic field is controlled to go by the iron core. Some of them will also go here round in the air, but that is just a minor. So basically all the magnetic field will follow the core, the iron core. But over here, when we have, for example, air, this magnetic field will go all the way around. And we can see here, this drawing is only in 2 dimensions, but we have to think that it is in 3 dimensions. So these magnetic fields are all the way around the coil. We have some terms over here, and the first one is the magnetic flux or magnetic field. And that is the number, you said it's the number of lines, magnetic lines out of the coil. Because if we increase the current in a coil, there will be more magnetic lines. So actually the magnetic flux is just the number of lines up here. It has the symbol phi, and the unit for it is Weber, capital letter W and lowercase letter b. The next one is magnetic flux density, or just flux density. That is how many magnetic lines do we have per square unit. So it is the magnetic flux divided by the area. You got it down here, magnetic flux divided by area. And the symbol is capital letter B, and the unit is Weber per square meter, and this fraction is called Tesla. So normally we said Tesla, and it has the unit symbol capital letter T. And if you heard about the unit Gauss, then 1 Tesla is equal to 10 power to 4 Gauss. Then again, we have a unit, permeability, or specific magnetic conductivity. It has the symbol, it's the Greek letter mu. So here it is actually the conductivity for the material, for example here in the core. And the conductivity for iron is much higher than air. It can be easily some 100 times better to conduct the magnetic field than air. And the permeability is equal to mi or micro 0 times micro relative. So it's the permeability, and the 0 is for vacuum, and we got a relative permeability here. So we just multiply a factor for a given material, how many times it's better to conduct the magnetic field than if we got space of vacuum. And this is a constant. It has the value 4 times pi times 10 power to negative 7. And a unit is volt seconds per amp meter windings. Sometimes we don't see this lowercase letter v for windings, number of turns in a coil, because it's actually not a SI unit, but I think it's okay to put it on. We know this one, we have seen it before nearly, for the capacitor, for the permittivity, and it just has the letter epsilon instead. So permeability, that's for a magnetic fields and how it can conduct. Then we have the magnetomotive force, F for force and M for magnetomotive. And there are many ways to calculate the magnetomotive force. For example, we can say it is I multiplied by N, and N is a symbol for numbers of windings and has unit V. So over here we can see it has a number of windings, and over here this has 1, 2, 3, nearly 4 windings. So we just multiply the number of windings and the current in the wire. Then we got the magnetomotive force for the coil. We can also use this one, Rm multiplied by phi, and phi was the magnetic flux. Rm, we can see it down here, it is the reluctance or the magnetic resistance, and up here it is the magnetic resistance in the iron core. And as we know from the resistor, for example for a wire, we can calculate the resistance depends on the length divided by the cross section area, or just area. And here we divide with the magnetic conductivity. For the resistor we could divide with the resistive conductivity or the specific resistivity. We can multiply. But this formula is nearly the same as for a resistor, but in this case it is a reluctance and it is the magnetic resistance. Finally, we have the field strength, capital letter H, and it is the flux density divided by the permeability. And we can see it up here. We use it when we calculate the magnetomotive force, and it is the field strength times the length of, for example here, the core. So the field strength multiplied by the length of the core, then we also got the magnetomotive force. Actually, this line, we can see there are many ways to calculate the magnetomotive force, and also we can find out, for example, the field strength. It must, if we have to isolate the field strength, we just can divide by the length over here. It must be the current times number of windings divided by length. So it must, the unit for it must be amp windings divided by meter. So that was just the basic words and knowledge of a coil.